Okay, Assalamualaikum warahmatullah. This is the fourth part of tutorial for chapter 6. Okay, we will try to solve this problem 6101. A commercial refrigerator with refrigerant 134A as the working fluid. So we know that our working fluid is refrigerant 134A. Is used to keep the refrigerated space at minus 35 degrees Celsius. So you have your space here, you want to maintain at 35 degrees Celsius. Okay. Remember, we have refrigerator. So you are taking heat from the cold space and then you throw out to the hotter space. Okay. So you have minus 35 degrees Celsius there. By rejecting the waste heat to cooling water, okay, this is the cooling water in the condenser there. Okay, enter the condenser at 18 degrees Celsius. That is the temperature entering, okay, the cooling water. You are given the rate of the cooling water mass flow rate, 0.25 kilogram per second. And going through the condenser or the heat exchanger, basically, okay, it will leave at 26 degrees Celsius. So that is the cooling system. The refrigerant enter the condenser. Okay, this is the condenser. So meaning that it will enter at this condition, 1.2 megapascal with the temperature of 50 degrees Celsius. And it will leave at the same pressure is constant, but subcool by 5 degrees Celsius. Okay, we will get to the term subcool a bit later. Okay, I will explain after this what does it mean by subcool. Okay, if the compressor consume, okay, you know that your compressor is 3.3 kilowatt, okay, of power. Okay, determine the mass flow rate of the refrigerant, the mass flow rate of this refrigerant. The refrigerant load, okay, refrigerant load basically is this QL dot, okay, COP of your system, okay, and the minimum power input to the compressor for the same refrigerant load. Minimum power input, remember when we say minimum power input, that will be ideal condition. So we can take that as when the system is reversible. Okay. All right, that is basically the problem that we have in hand. Okay, let me get back to the term subcool. I think I have not mentioned about subcool before. When we say same pressure, but subcool by 5 degrees Celsius. What does it mean by subcool? Meaning that the temperature is lower than the saturated temperature. Okay, already that it is already in the compressed region, and the temperature is lower by 5 degrees from the saturated. So you can check in the table. The pressure is given 1.2 megapascal. You can find the saturated temperature. So the subcool temperature, in this case by 5 degrees, you just simply minus the T saturated from the from 5 degrees. So it is 5 degrees below the saturated temperature, basically. Okay, so there are two things there. Basically, heat is transfer. Of course, you are taking heat from the what we call that cooling space, and you are throwing. This is your QH dot. We have QL dot here, taking from the refrigerated space, and then you throw out the Q in the condenser. You are throwing to the cooling water. So cooling water is being heated up, taking the heat from our system. Okay. So there is an exchange of heat from the refrigeration, from the working fluid, refrigerant 134A, to the water, basically. So we can say that QH dot, okay, actually you can relate between the two conditions. QH dot is nothing but the mass flow rate of the refrigerated. Okay. Looking into, let's call this as state 1 and this is state 2. Okay, let's put a circle on that. Okay. So in that case, then the QH, okay, the rate of heat transfer is nothing but m dot of the refrigerated, okay, or refrigerant. Of course, we can relate between the H. So in this case, then generally when we say delta H is H2 minus H1. Okay, but we know that heat is leaving the refrigerant, so you are losing the heat from your refrigerant. By right, H2 is lower than H1. So if you do this, then you will get negative value because energy is dropped or released from your refrigerant. So H2, we can expect that to be lower than H1. So one way to do that, either you switch this, okay, or you just put negative value there. Okay, negative to indicate that. Just to take the direction we know already, then we will have a positive value. So you can, you can rewrite in terms of, this is nothing but that mr dot H1 minus H2. Then you will get positive value. Okay, we know positive value in this case is either positive or negative. It is basically heat transfer. It just that it indicate the direction. Negative indicate that it is leaving your system. But anyway, let's put in that way, whichever that may you are happy. Okay, doesn't really matter, but you need to know the direction. Then, so long that you understand, then should be okay. But at the same time, you can also relate the heat transfer from the cooling water. Okay, because you know that the same amount of heat is leaving the system but going to the water. So it is also nothing but m of water, m dot mass flow rate of the water. Okay, we need to label also here. Let's call this as inlet and this is as outlet. Okay, I and O indicating inlet and outlet, or you can have IO and E. Inlet and exit, doesn't really matter, whichever that you feel comfortable. So in this case, then you know that it is, we are talking about the water part. So outlet HO minus HI. In this case, it is correct. HO will be higher than HI because now heat is transferred to the system. You would expect that H will increase. Okay, the outlet, outlet will have higher enthalpy compared to the inlet. So these two is you can relate. They are the same in terms of the Q dot value. Okay, take note of that. So the first part, the mass flow rate of the refrigerant, we are not given that, but we are given the mass flow rate of the water. So you can see that if you solve this, you will get this Q dot H. So having Q dot H, you can also find H2 and H1 based on the property. Then you can find the mass flow rate of the refrigerant. Okay, so basically that is the idea, what we are trying to do. Okay, now let's analyze the water part. Water comes in at 18 degrees Celsius. Usually the water will have the atmospheric pressure. So you know that it is not boiling. It is not even in the saturated form. 18 degrees Celsius, it is in compressed liquid condition. So let's look at for cooling water. Okay, so you say that it is in compressed liquid form. What about the outlet? Outlet is 26 degrees Celsius, also way below the 100 degrees Celsius for boiling. So you can say that inlet and outlet, they are both in compressed liquid form. Okay, and it is water, so you can you have A4, A5, and A6 also. But compressed liquid usually then you don't have for atmospheric pressure. If you check the table, then you don't have that. So you know that you can have approximation. Remember the for compressed liquid, the property can be estimated to be around the saturated liquid. at the temperature. So inlet, okay, inlet is 18. So temperature of the inlet, oops, okay, the temperature of the inlet, which is in our case is the 18 degrees Celsius. Okay, similarly for the outlet, then because both are in compress, so outlet can be estimated to be the saturated liquid at the outlet. Okay, let's go to the table. Okay, if you refer to your table, let me go to my table. Okay, oh, okay, this is refrigerant. We need to go to the A4 because temperature. Okay, because we are estimating based on the temperature. The variation is not based on pressure. Okay, you can see that we have, going back to our problem, our inlet temperature is 18 degree and outlet 26 degree. We are talking about the water, cooling water coming in at 18 degree, going out at 26. Let's look at the table. Unfortunately, we do not have 18. 18 is between 15 and 20. And even 26 is not also in the table. So you have to interpolate. So you can see that the inlet is interpolation between 15 and 20. You need the HF. Okay. The other one just next to it, 25 and 30. Okay. So let me summarize, going back to our figure, our problem. Okay. From table A4, okay, you can see that your temperature and your H, okay, this is kilojoule per kilogram. You can see that we have 15, and then our problem is 18, the inlet, and then you have 20. Okay, if you refer to the table, the H is 62.982 or 15.982. Of course, this one is our inlet. Okay, 20 is 83.915. 83.915. Okay, you can continue. Let me just combine the table. 25, and then we are trying to find for 26, but the value in the table is between 25 and 30. So 25 is 104.83. This is our HO, and 30 is 125.74. Okay, so basically we have to do two interpolations, okay, from the same table. So HI is nothing but from the first three there. Okay, HI is nothing but 62.982. I just rearranged the interpolation already, but you can always do from the beginning. Okay, which is nothing but 18 minus 15 divided by 20 minus 15. Okay, multiply by 83.915 minus 62.982. Okay, that should be the relation. Okay, if you calculate this, your HI would be 75.54 kilojoule per kilogram. Okay, do the same for HO. HO is 104.83. My writing is getting worse. Okay, let me rewrite. 104.83 plus you have 30 minus 25. Bye-bye. Oh, no, that's not right. That should be the denominator. Let me just 26 minus 25 divided by 30 minus 25. Okay. That's the ratio. And then 1 to 5.74 minus 104.83. Okay, and again, if you do that, then your answer, you'll get it to be 109.01 kilojoule per kilogram. So we have already Hi and H naught. We have m dot W given 0.25 kilogram per second. So you can find QH. Okay, dot. Therefore, QH dot is nothing but MW dot H out minus H in this case, 0.25 kilogram per second. H naught is 109.01, 109.01 minus 75.54. Value is kilojoule per kilogram. So cancel kilogram, you have kilojoule per second. And that value turns out to be 8.367. 8.367 and kilojoule per second. So that will be the QH. But the question part A is actually to get the mass flow. Okay, this is part A. We are talking about part A. And we have that value. Now we can relate with MR, but we need to also find H1 and H2. Okay, now we have to go to refrigerant 134A. If you go to table, remember the condition at 1. Okay, let me, before going to the table at 1, okay, we have pressure equals to 1.2 megapascal. Okay, temperature equals to 50 degrees Celsius. So we need to check what would be this condition. Let's go to the table. If you go to the table, now we have to go to refrigerant. Let's go to saturated refrigerant table, which is a given for pressure. Let's go with the pressure. Yeah, A12. Okay, 1.2 megapascal, 1.2 megapascal is this one. And you can see that the temperature, saturated temperature is 4629. Okay, and ours is 50. Okay, from A12, T saturated is 46.29 if I'm not mistaken. Let me check again. 46.29. Yep. Okay. Degree Celsius, which is less than temperature of our state. Therefore, okay, we know that this is in superheated region, vapor. Okay, already in superheated vapor, it goes already beyond the saturated temperature. So now we have to go to table A3 from A13. Okay, the superheated vapor for refrigerant. If you go to A13, for pressure is 1.2 megapascal, saturated for 6.29, and our temperature is 50. Okay, so we don't have to interpolate. It is there, 50. So from 50, your H is this column, 278.27. Okay. So we can just simply take H1 is equals to 278.7 kilojoule per kilogram. So you have already conditioned H1. We need to find H2. Okay. H2 mentioned here, it is subcool. So subcool already, as I mentioned before, subcool meaning that it is lower than the saturated. So it is already in compressed. At 2 compressed liquid. Therefore, you can estimate the H. Remember, we can estimate H, which is H2 in this case, is equals to H of saturated liquid at the temperature, okay? Temperature T2, okay? But we need to know what is T2. All right, so we can use this equation. T2 is nothing but, as I mentioned earlier, is when we say subcool, is the temperature below the saturated temperature. So T2 is nothing but T saturated minus subcool temperature, 5 degrees Celsius. So you have 46.29 minus 5. So you end up with 41.29. Okay, to 9 degrees Celsius. So that will be your temperature at 2. So refer to the table. Now you have to go to table of saturated table of refrigerant for 1.29. Let's go to the table saturated but with temperature, not with the pressure, not A12 but A11. A11, okay, because we are estimating at temperature and our temperature is 41.29. Temperature for okay, again, we have to interpolate. Okay, we have 40 and 42. Okay, all right, so refer to this. So you are interested in the HF, okay, the saturated liquid condition. So you need to interpolate from table A11, interpolate. Okay, you have T 40 and ours is 41.29 or 41.3 if you want to put it simplify, and H is 108.26 and H2, and the other one, if you refer to the table, is 111.26. Okay, so from here, if you interpolate, you have H2 equals to 108.26 plus 41.3 minus 40 divided by 42 minus 40 multiplied by 111.26 minus 108.26. Your H2 turns out to be 110.19 kilojoule per kilogram. All right, so we have H2, we have H1. So we can go back to this problem, go back to this equation. You know that Q H dot is equals to, already we calculated 8.367, 8.367 K kilojoule per second is nothing but equals to R dot, the one that we want to find out, H1 minus H2. H1 is 278.27 minus H2 110.19. Okay, all known except MR. Therefore, you calculate this, you have the mass flow rate of the refrigerant. If you calculate this, it turns out to be 0.0498 kilogram per second. Okay. This is mass flow rate, kilogram per second. So that is your answer for part A. Okay, a very long process for part A. Let's go to, then we can go to B. Okay, the rest will not be Oh boy. Keep. What's wrong? Okay. Okay. I believe we are still, let me check somehow. Yep. Okay. Well, let me just put it somewhere here. Okay. All right. Part B. B is the refrigeration load. Not too difficult. Refrigeration load is QL there. Okay. And you can relate with the energy balance. You know already. Okay. We have basically from the system, QH is leaving, QL and W is coming in. So basically your QL dot is equals to QH minus W in dot. Okay. I hope you don't have any problem with that. That one is based on our energy balance equation. And we have already everything. QH calculated earlier, 8.367. Of course, kilojoule per second. Minus work in is also 3.3 kilojoule per second, which is kilowatt. Okay, so you know the unit here will be 5.07 kilojoule per second. Okay, so that would be simply the answer for B. Okay, simple. C, the COP just go to the equation. COP for refrigeration is nothing but you are interested in the load, okay, QL, and compare with the work in. Everything is given. QL just calculated 5.07 divided by work in is 3.3. Check the unit, both are kilojoule per second. Okay, so from here you can say that it is 1.54. That is your coefficient of performance for the refrigeration. Okay, not too high, above, just slightly above 1. Okay, all right, the last one, the minimum power input to the compressor for the same refrigeration load. Okay, the minimum is when we have minimum is when process is reversible. So in that case, your COP for refrigeration is nothing but 1 over TH over TL minus 1. Okay, that would be the equation. Okay, but what about our TH and TL? We know TL will be the temperature at the lower. Temperature at the lower, we are talking about to keep the refrigerated space of minus 35 degrees Celsius. So basically, let me use this space. We have our aircon or refrigeration here. You have load work in. You have QL, okay, and from a outside space, okay, outside already cold. Oh, well, sorry, this one is more proper. It's not the outside, basically the refrigerated space. Okay, let's call that as space, and we throw out to the our outside. Okay, this is the space that we want to cool. So you are taking the QL from there, and you take the QH and throw to the outside. And this is your TL, and this is supposed to be your TH. Okay, so that is the relation that we have. So TL is simply minus 35 degrees Celsius. What about TH? TH is actually our outside is the water. Okay, 18 degrees Celsius. This is where you have that exchange of the heat. Okay, that should be the water in the reservoir outside. Okay, where you throw the heat. So your relation will become 1 over TH is 18. And remember again, COP and efficiency, you have to use Kelvin. So 18 plus 273 divided by minus 35 plus 273, okay, minus 1. So that is your equation. Okay, so 1 divided by this relation. If you do this, then you can see that the minimum power input is 4.49. Oh, sorry, this is not the power. We are talking about the for minimum or for visible process, this is the coefficient of performance. We have not done yet. In terms of the power, you need to relate. Let me use this small space here. I don't have much space. The work in minimum minimum is equals to work in reversible. Okay, it will be minimum when the system is reversible. So remember, we can relate again with the COP. COP is Q L and work in there. So work in is nothing but Q dot L divided by COP. Okay. So in that case, let me put QL over COP. Right. In this case, okay, for reversible, okay, that would be the relation. So you have 5.07. Okay, the Q dot L divided by COP, we just calculated 4.49. So calculating this, it is 1.13 kilowatt. Right, I'm using all the space already. So that would be the minimum work required, which is 1.13. The one that we are using in our system is 3.3. This is because our system is not ideal. There are there are many irreversibilities. But if your system is ideal or reversible, then the work required is only 1.13 in order to perform as such. Okay, I think that should be all for this particular problem. If you have any question, then ask me during class next time. Okay, and I think that's all. Thank you. Assalamualaikum.